You know that feeling, right? You shuffle your feet on the carpet, you reach for a doorknob, and zap, you get a little shock. Or maybe you pull a sweater over your head, and suddenly your hair is standing straight up. That's static electricity. It's so common we barely even think about it. But behind that familiar little spark is actually one of the most powerful and fundamental forces in the entire universe. So today, let's crack the code.
Now think bigger, way bigger, because that exact same force, on a much grander scale, can create something as absolutely terrifying and beautiful as a bolt of lightning. This is pure, raw electric force, and it is no joke.
So, what is this invisible force? I mean, how can it be powerful enough to literally tear the sky apart, but at the same time, it's gentle enough to make a balloon stick to a wall?
And yeah, it's the very same force that causes these styrofoam pewits to cling mercilessly to this poor cat. It's not some kind of magic, and it's definitely not gravity. It's something else entirely, all based on a fundamental property called charge.
From the cosmic scale of lightning down to the comical level of static cling, all of these things are governed by the exact same set of rules. And our goal here is to figure out what those rules are, to really understand how this invisible, everyday force actually works.
So this thing is called the electric force, and here's the deal with it. It's what we call a non-contact force. That means objects don't actually have to be touching to push or pull on each other. And, kind of like gravity, its strength fades the farther away you get. But trust me, that's pretty much where the similarities end.
To really get this force, we have to talk about where it comes from: electrical charge. And what's so cool is that we can uncover a deep, fundamental secret of the universe using, believe it or not, nothing more than a couple of strips of regular old tape.
Okay, here's how you do it. You basically make a tape sandwich. You put a bottom strip down, then a top strip right over it. Then you rip the top strip off the bottom one really fast. When you do that, something amazing happens. You've just created two different kinds of charge tape, a T-strip and a B-strip. And now for the magic. If you bring two of your T-strips near each other, they actually push apart. They repel. The same exact thing happens with two B-strips. But when you bring a T-strip and a B-strip close together, they pull towards each other. They attract. This simple little observation tells us something truly profound about how the universe is built. What this little experiment proves is a core principle of our entire universe. There are two, and only two, types of electrical charge. Everything in the universe that has a charge is either like that T-strip or it's like the B-strip. There's no third option. We just call these two types positive and negative.
And this leads us directly to the fundamental rule, the one simple principle that governs every single electric interaction there is, from the atoms inside your body to the stars up in the sky.
And it's beautifully simple. Like charges repel and opposite charges attract. That's it. Two positives will always push apart. Two negatives will always push apart. But a positive and a negative, they'll always pull together. This one little rule is behind everything from how molecules are built to why your socks stick together in the dryer.
Okay, so we know what happens. But in science, what is only half the story? The other, really important half is how much. How strong is that push or pull? This was the huge question back in the 18th century, and it set scientists on a quest to actually measure this invisible force. So, thinkers like Joseph Priestley had a hunch. They guessed it might follow what's called an inverse square law, which is just a fancy way of saying the force gets weaker really fast as you move away, kind of like how light from a candle gets dim. But it was a French physicist named Charles Coulomb who, in 1785, painstakingly measured the force and proved it. And his incredible work gave us the blueprint, the mathematical formula that lets us calculate the electric force between any two charges, anywhere in the universe. And of course, we call it Coulomb's law.
And there it is. That's the one. That's the equation that cracked the whole code. It might look a little simple, but every single part of it tells us something absolutely critical about how our world works. So let's break it down real quick.
So F, the force, depends on the amount of charge on each object, that's Q1 and Q2. Basically, more charge equals more force. It's also inversely proportional to the square of the distance, r. All that means is if you double the distance between the charges, the force gets 4 times weaker. And it's all multiplied by this special number k, which basically tells us just how incredibly strong this force is. And that constant, that k, is the real key here. Because when you actually run the numbers, you discover something that is just, well, it's astonishing.
The electric force isn't just a little bit stronger than gravity, it is almost incomprehensibly stronger.
I mean, just look at how similar the two laws are. They both have that same inverse square thing going on. But gravity depends on mass and can only ever pull things together. The electric force, on the other hand, depends on charge, and it can either pull things together or push them apart. And that constant K is it's astronomically larger than gravity's constant G.
So, to really put this into perspective, let's ask a simple question. Think about a hydrogen atom. It's just one proton and one electron. Now they both have mass, so gravity is trying to pull them together, and they both have charge, so the electric force is also trying to pull them together. Which one wins?
Yeah, it's not even a contest. It's not even close. The electric force is stronger by a factor of 10 to the power of 39.
That number? I mean, what even is that? It's 1,000 billion 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 billion. The number is so big, it's practically meaningless to our brains. The gravitational pull between that proton and electron is so tiny it's completely irrelevant. This is why a little bit of static on a sweater can make your hair stand up, easily overpowering the gravitational pull of the entire planet Earth.
And this leads us to one last fascinating puzzle. If the electric force is so mind-bogglingly powerful, why does it seem like gravity is the one running the show in our everyday world? Why does gravity hold us to the Earth and keep planets in orbit? Well, the answer is all about balance. Because unlike gravity, which only ever pulls, electric charge comes in those two flavors, positive and negative. And in most big objects like you, or me, or a planet, those charges cancel each other out almost perfectly. And that leaves the much, much weaker force, gravity, to take center stage. And it's that perfect cancellation that makes our universe stable at all.